Hello, welcome to the study guide or test for intermolecular forces. In this, we have some questions. Up at the top, there is a title, which is going to correspond to one of the videos that are on this channel. So if you find that some of these questions are just a little tough, you're not really sure what they're asking, make sure to go back, check out that particular video, rewatch it, relearn it, maybe hear it a second or third time, and then these questions should be a little bit easier. To begin, answer the following questions. What's the difference between a polar and a nonpolar bond? And then of those 6 bonds, which are polar and which are nonpolar? In covalent bonds, electrons are shared between 2 atoms. So in a polar bond, that sharing is unequal. One of the atoms is going to have the electron more often, more of the time, than the other. When this happens, you are going to create partial charges because one of your elements is a little bit more negative than it usually is due to that electron hanging out with that element. The one that's negative is going to be the one that has the higher electronegativity, and obviously the positive is going to have the lower electronegativity because it doesn't have the strength to hold on to that electron. A nonpolar bond is the opposite, and that is one that has no poles, no positive or negative charges, and that is due to equal sharing across the bond. So a hydrogen-bromine bond is going to be polar because bromine has a much higher electronegativity than hydrogen. Hydrogen bonded to another hydrogen or chlorine bonded to another chlorine, those are both going to be nonpolar because both of the atoms in the bond have the same electronegativity. We can also describe this as them being symmetrical. Because they are symmetrical, they don't have an advantage one side over the other. Sulfur bonded to hydrogen is not super polar because their electronegativities are pretty close, but they're not the same. So that will be a polar bond. Oxygen bonded to fluorine, of course, is a polar bond. Really, anything bonded to fluorine is going to be a polar bond because fluorine has a super high electronegativity. And then lastly, we have sodium bonded to chlorine, which was kind of a trick question. Sodium is very willing to give its electron, and chlorine is very willing to take it with a pretty high electronegativity. So it's not a polar bond. They're not sharing electrons. It's kind of so polar that it actually becomes ionic. It's a full transfer, so you have full charges. Then we get into molecule polarity. So the first question, what is the difference between a polar and a nonpolar molecule? And then of the following molecules, which are polar and which are nonpolar? Polar molecules have asymmetrical charge distribution, which is going to put charges on the molecule. You'll have a region that's a little bit more negative than another region on the molecule, which would be positive. Nonpolar molecules are symmetrical across the board, so they have no specific area or region that is more negative than another. And typically we can figure that out just by looking at the picture. So we have nitrogen bonded to nitrogen, diatomic nitrogen or a nitrogen molecule. That's totally symmetrical. So because we have the same number of electrons on each side, the atom is even the same. So the electron cloud for that atom is the same on both sides. That would be a nonpolar molecule. Then we have hydrogen bonded to iodine in hydroiodic acid. And you need to remember that iodine has 53 electrons in its electron cloud. Yes, and hydrogen only has 1, and iodine is trying to take that 1 electron. So iodine is very negative compared to the hydrogen, making that a polar molecule. Then we get into PCl3, which is phosphorus bonded to 3 chlorines, and this is going to be a trigonal pyramidal shape, meaning that the phosphorus has its lone pair like sitting on top of it, and then the chlorines are going to pop down almost like they're legs of a tripod. So the molecule is lopsided just from that alone. You have a lone pair on top and no lone pairs on the bottom. So what's going to happen is that this is lopsided. You'll have a negative charge and a positive charge on this molecule, making it polar. And the same is true for water. The hydrogens collectively are the positive region, and then the negative electrons on the oxygen collectively make that area very negative. Also, oxygen's electron cloud is much larger. That's going to be the partially negative side, and that will give you a polar molecule. One of my favorite questions to ask on the intermolecular forces test is this: how is it possible to have a nonpolar molecule that has polar bonds? When this question is asked, carbon tetrachloride comes to mind for most chemists, and that is because this molecule is entirely nonpolar. It's absolutely symmetrical, but if you were to zoom in and just look at one of the carbon-chlorine bonds, that's superpolar. In fact, the chlorine is really tugging on those shared electrons. So this chlorine is going to be partially negative. But the reason that this is a nonpolar molecule is because in all directions, carbon's shared electrons are being pulled away equally. So the fact that this molecule is symmetrical is what makes it nonpolar, even though the carbon-chlorine bond is very polar. Here we are getting into intermolecular forces. The first question: what is a dipole-dipole force? What type of molecule participates in dipole-dipole forces? And how can a dipole-dipole force upgrade to a hydrogen bond? Dipole-dipole force is an interaction, a force of attraction between polar molecules. The positive side of one molecule will be attracted to the negative side of another. So this force of attraction occurs only in polar molecules, and the only way to upgrade a regular dipole force into a hydrogen bond is the contents of the molecule. So the molecule must have a hydrogen in order for this to work, but it also will have to have either a fluorine, an oxygen, or a nitrogen. Common examples of molecules that hydrogen bond are water, ammonia, and hydrofluoric acid. The next question here: what is a dispersion force? And then it asks you to use the halogens to explain how the number of electrons affects the strength of an intermolecular force. I would anticipate that most high school chemistry tests are going to ask about the halogens, so make sure that you know that one. A dispersion force is a weak force of attraction caused by temporary partial charges on molecules when their electron cloud shifts around. So when molecules bang into the walls of their container or other molecules, their electron cloud warps. You'll have a region that has a little surplus of electrons for a short amount of time, and that's going to be your partial negative. And that's a temporary charge because the nucleus is going to rearrange all those electrons back to kind of where they're supposed to be. The reason we use the halogens a lot is because not only are they nonpolar bonds, but they are also nonpolar molecules. So they're really great for this. The dispersion force is really based on, or rather the strength of the dispersion force is really based on the size of the electron cloud. So if we look at fluorine, and we're looking at a fluorine molecule specifically, we would have 18 electrons and a really high electronegativity on fluorine herself. When we check out iodine, still a halogen, a few rows down, iodine is going to have 106 electrons in its molecule, and it's way bigger. And it also has a lower electronegativity because it's bigger. So that electron cloud is going to have way more warping, and the temporary dipole is going to last much longer in iodine than it does in fluorine. So because fluorine has fewer electrons and is able to reel them back in really quickly and kind of get them into their nonpolar configuration, it's going to be a lot less strong than the force of iodine, who really struggles to get those electrons back to where they belong. Here we have a few molecules. Just looking at the Lewis structure, you should be able to figure out whether it is polar or nonpolar, and then figure out what type of intermolecular force is used by each of those molecules. It's important to note that all of these molecules will have dispersion forces, and that is because all of them have electron clouds. When you have polar molecules, the dispersion force is really only going to account for a little bit of the strength of the intermolecular force. It's kind of outshadowed by the dipole-dipole or the hydrogen bond. So in the nitrogen molecule, we have dispersion forces only because it's nonpolar. The only way you're going to get an IMF from N2 is from the warping of its electron cloud. PCl3, we've already determined, was a polar molecule, and it has dipole-dipole forces because it's polar. It has a positive region and it has a negative region. And for that reason, the dipole-dipole force is going to be the primary force, although it still does have dispersion forces. The same is true for hydrogen bonded to iodine. In that case, again, you have a polar molecule, so it will have dipole-dipole forces. It will also have dispersion forces, but those are far less significant than the dipole-dipole force. And then finally, we have water and ammonia, which are both polar molecules, but they have the special hydrogen plus an oxygen in water and a nitrogen in ammonia. So for that reason, those are both going to exhibit hydrogen bonding as its primary intermolecular force. Now we're getting into the effects of intermolecular forces. So the next question, how would you describe the physical properties of a compound with weak intermolecular forces like acetone? Because acetone has a weak intermolecular force, it's super easy to separate its molecules, meaning that the boiling point is going to be very low. It's super easy to get this thing to boil. It's going to have a low melting point. It's very easy to melt. And it's going to have a very high vapor pressure, which means that it loves to evaporate. Conversely, how would we talk about the physical properties of a compound with strong intermolecular forces, perhaps like rubbing alcohol? If a substance has strong intermolecular forces, it means they really want to stick together. So you're going to have a hard time separating the particles. So its boiling point is going to be super high. It doesn't like to boil. It would rather be a liquid. When it comes to melting, the particles really want to stay together in the solid phase. And when it comes to vapor pressure, the willingness of a substance to evaporate, it doesn't want to evaporate. It has a very low vapor pressure because it doesn't want to evaporate. Okay, final question. Again, this is something that comes up on a lot of high school chemistry tests. And in this case, we're comparing hydrogen sulfide, which is H2S, to H2O. Important to note here that oxygen and sulfur are in the same group on the periodic table. So the question is, the boiling point of water is 100 degrees Celsius. The boiling point of dihydrogen sulfide is negative 60 degrees Celsius. Why is the boiling point of water so much higher than H2S? Although both of these are polar molecules, water exhibits hydrogen bonding as its primary intermolecular force. So it's going to have a stronger force than H2S, meaning that it takes way more energy to get it to boil. It's going to have a much higher boiling point than dihydrogen sulfide. And that's it. That's everything. If you have any questions, please leave them in the comments section below the video. Make sure that if any of the questions were a little tough for you, to go back, check out the title of that slide and go back to that video, kind of review the content and make sure you feel good. Subscribe so that you don't miss the next lesson, and I'll see you there. Bye.